All right, guys, welcome back. This is our lecture on section 2.2 with matrix operations. This is really the basic operations for matrices. We're going to talk about addition, subtraction, multiplication, things like that. So there's not a lot of prerequisites. Arithmetic, just being able to do basic arithmetic, and of course, matrix terminology. All right, so hopefully you've viewed the lecture on matrix terminology so that when I use some of these words and notations, you won't get lost. Okay. All right, so this is not really that bad. And in point of fact, two of these operations are defined almost exactly the way you think they would be. Okay, so let's go ahead and start with addition. Okay, so let's start with addition. So let me make up a matrix here. So I've got 1, 3, 0, 4, negative 1, 1. Okay, and I would like to add that to 2, 2, negative 1, 4, 1, 3. Okay, so, and again, intuitively, if I were to add these two things together, the most natural thing is, well, what if I just add the corresponding, components here? And that's exactly how we do this, right? So if I want to go ahead and add these two matrices together, if I want the 1, 1 entry in the sum, I just take the 1, 1 entry from each of these and add them together. So 1 plus 2 gives me 3, right? And do the same thing here. 3 plus 2 gives me 5. 0 plus negative 1 gives me negative 1. 4 plus 4 gives me 8. Negative 1 plus 1 gives me 0. And 1 plus 3 gives me 4. Okay? And that's it, right? So let's talk, we'll troubleshoot a little bit. Where do people make mistakes on this? It's trying to go too fast, right? Okay? This is just 6 very simple addition problems. And I'm very fond of saying there's nothing in this world you can get right 10,000 times in a row, right? Yeah. And that's just, every now and then you'll make mistakes. Just be methodical and be very, very detail-oriented, and this should be fine. But this brings up an interesting concern, okay? So these two, again, perfectly natural, but how would I add these two together? Well, I could add the corresponding components, but then when I get down here, I don't have anything to add them to. So it turns out this doesn't work. You can't add these two things together, right? So this first matrix in this particular sum is a 2 by 3. Nope. 3 by 2. My bad. All right, it's a 3 by 2. This one's a 2 by 2. If they're not the same size, then this operation is not defined, right? So this is not defined. Okay, this is an undefined operation that I don't know. This doesn't have a result, right? So when we add, we have to add things that are the same size, right? That's a bit of a restriction. Since my matrices can be any given size, they got to make sure they're the same size to add them together. But beyond that, it's fine. Okay. The other good news is all the properties that you can think of with addition still hold. Still associative, still commutative, right? All these things are very nice. So all the properties with real numbers and addition hold with matrices. And addition, provided, of course, you can actually add them together. Okay, fine. So let's get slightly more complicated here. Not a lot, just a little bit. Okay. So I'm going to leave my example matrix here. How about multiplication? Well, there's a couple different kinds of multiplication. Okay. I've got matrix multiplication, which is a matrix times another matrix. I'm going to leave that until later on in the lecture. And I've got scalar multiplication, where I multiply a matrix times some scalar value. Okay. In this particular case, I am going to choose, let's say, -3. Okay. So I'm going to multiply this matrix times -3. And again, let's go back to what does our intuition say? What would be sort of the logical thought process for doing this? Well, it sort of looks like I should just distribute this scalar to every entry inside the matrix. And yeah, that's exactly what you do, right? That's exactly what you do. Okay, so here we go. -3 times 1, that's -3. -3 times 3 is -9. -3 times 0 is 0. -3 times 4 is -12. -3 times -1 is +3, and -3 times 1 is -3. Same concerns with going too fast as before. Okay, we're not doing complicated arithmetic here, but if I make you do it enough times, then eventually you'll mess one up. Okay, and we want to try to avoid that. Okay, again, very intuitive, very straightforward. This seems perfectly reasonable. Okay. By the way, I'm going to give you the index definitions for all of these things at the very end. Okay. All right. So let's see. With scalar multiplication and addition, we now have a way to define subtraction. Okay. So we now have a way to define subtraction. Okay. Suppose I have a matrix A. I would like to subtract matrix B. Again, there's an intuitive way to think about this. You subtract them component-wise, just like you would for addition. And of course, we can get there by just rewriting this as A plus the scalar -1 times B. Okay? Fine. So again, this allows me to perform this operation, but again, it's the intuitive one that makes a little bit more sense, right? Yeah. So again, let me go ahead and subtract. I don't know. Work an example here. 1, 1, -1, -1, 4, 2. Sure, why not? Okay. Again, got to be the same size, because if I'm going to subtract them component-wise, they'll need to be the same size. Let's just go ahead and go through it very quickly. Okay. Again, to get the 1, 1 component, you subtract the 1, 1 component. So 1 minus 1 gives me 0. 3 minus 1 gives me 2. 0 minus -1 gives me +1. 4 minus -1 gives me 5. -1 minus 4 gives me -5. And 1 minus 2 gives me -1. Okay? And this is fine, right? This is fine. This is, again, all three of these things we've done so far, addition, scalar multiplication, and subtraction, are exactly what you would assume they would be. And all of them work exactly the way they would for real numbers. All the same properties hold, right? Addition, commutative, associative, scalar multiplication. Okay, it's commutative. You have the distributive property, right? If I have some scalar times A plus B, it's the scalar times A plus the scalar times B. Okay, all those things hold. Everything works fine for those things. Subtraction, well, subtraction for real numbers is not commutative, so obviously it's not commutative here. You don't gain any properties, but you don't lose any either. This is all fine. The problem comes in, actually, when we start talking about multiplication. Actually, well, sorry, let me introduce one thing before we jump into multiplication. One more thing. So when we talk about an operation like addition, okay, we want to talk about something called the identity, right? So in any of these operations, of course, you want to identify the identity. What is the identity element? Okay. The identity element is the element that can be utilized with that operation to affect no change, right? So for example, just show you for, let's say for real numbers, if I say 3 plus some real number and it affects no change, so it's still 3 after I add, what was that number? Well, the number had to be 0, right? Yeah? So it had to be 0, and in point of fact, 0 is the identity for addition, for real numbers, right? Same thing, okay? We'll talk about, let's say, multiplication. So I've got 7 times some mystery number, and there's no change, it's still 7. So again, there's an identity element here, right? The identity element for multiplication is, of course, 1, right? 7 times 1 gives me 7, right? Which gives to the generalizations, anything plus 0 is itself, and anything times 1 is itself. Okay, that's fine. Okay. Well, let's talk about the identity element for addition, which of course would be the same thing for subtraction. Okay. Well, what's the identity element? Well, that depends on the size of the matrices, right? So for instance, let's say I've got A, which is a 4 by 3 matrix, and I'd like to add another matrix, and the result I would like to still be the same A, right? Let's think about what we're doing here. If I add every component of this matrix to its corresponding component, and I don't want any of those components to change, well, then what does that tell me about the entries for this matrix, the mystery matrix? Well, they all have to be 0, right? If any one of them was non-zero, then it wouldn't be the same matrix at the end. And so what we have here is we have what's called the 0 vector, or the 0 matrix, or the 0 for addition, right? For addition, when we say the 0, we mean the identity element for that addition, right? That's the 0, okay? Now, the reason why I have to say the 0 is because the identity for, let's say, 2 by 3 matrices, okay? So the additive identity for 2 by 3 matrices, well, that is the 2 by 3 matrix that has 0 everywhere, right? This is the 0 vector. This is the 0 for adding 2 by 3 matrices. But the additive identity for, let's say, 3 by 3 matrices, well, that's just going to be the 3 by 3 matrix, again, with zeros everywhere, okay? And again, that makes sense, but the thing I want to point out here is these are not the same matrix. This is not the 0 matrix for the 3 by 3, right? So we don't just have one 0, we have a 0 for every possible size of matrix, right? Yes? And that will be the relevant 0 to add. Now I should point out that we don't typically specify that. Since every 0 matrix is the matrix with zeros everywhere, then what we do is, when we write this algebraically, we just put this 0 with the vector symbol over the top of it to indicate that I'm adding the 0. Which 0? Well, whichever one is relevant at this point in time, right? So in this particular case, for this expression, we just assume that this 0 is the 4 by 3 0 matrix to make this make sense. Does that make sense? So that's the identity. Does that make sense? Now, the important thing to remember here is, again, we no longer have one identity, we've got many, and we'll have to track which one we're using at each point in time. Okay, so let's talk about multiplication. Okay. there is an index form for this. I do not want to write it down first because I don't feel like it helps when learning how to do this operation. What I would like to do actually is I would like to show you an example first, okay, and see if we can't work through what's going on. So so this is matrix multiplication. And let me work an example first. So let's take the following matrix. 2, 3, negative 1, 1. And I would like to multiply it times, let's say, 1, 2, negative 5, negative 2. Okay. All right, now the question is, how do I do this? Okay. So hopefully you guys remember dot products, right? And if you don't, here's a quick definition here. So let's say I have u1 comma u2. I'd like to take the dot product with v1 and v2. Okay, this is what you do is you multiply the corresponding components and you sum the result. Okay? Yeah. So it's u1 times v1 and then u2 times v2 and you add them together, right? So I'm going to take the product of these two matrices by doing a lot of dot products. Okay? So here's what we do. Let's take my very first entry right here, which is A11, okay? Okay. A11 is row 1, column 1, okay? Row 1, column 1. So A11 in my product, okay? This first index, row 1, second index, column 1. Okay. In order to get A11 in my product, what I do is I take the dot product of row 1 from my first matrix and column 1 from my second matrix. Again, row 1, column 1. That's it. Right? So in this particular case, okay, that would be the dot product of 2, 3, and 1, negative 5. Okay? Again, row 1, dot, column 1. Okay. Now, let's go ahead and work that out. That's 2 times 1 plus 3 times negative 5. Okay? That's 2 minus 15, which gives me negative 13. Okay? And so A11, the value for A11 in my product is negative 13. Okay, does that make sense? Okay. How do you think we're going to do A12? Okay, so this next entry, that's A12. Well, A12 is row 1, column 2. So the dot product I'm going to take will be the dot product between row 1 and this time column 2. Okay? All right, well, row 1 is still 2, 3. Column 2 is 2, negative 2. Okay? So I get 2 times 2 plus 3 times negative 2. That's 4 minus 6, which is negative 2. So A12 is negative 2. This seems perfectly reasonable, doesn't it? Okay. Yes, it does seem reasonable. However, I can't keep doing this, right? We're about halfway through, and it's taken us 90 seconds, like a minute and a half, and we're only halfway through, and this is only a 2 by 2 product. I need to be able to do this for matrices that are like 5 by 5, right, or 6 by 6, and I can't write all this crap out, okay? So unfortunately, one of the things that you're going to have to do is that you're going to have to generate an aptitude for being able to do these things in your head, or at least with a minimal amount of writing. Otherwise, they're going to take forever. Okay? Now, this is where people end up messing this up a little bit. This is a 2 by 2 matrix times another 2 by 2 matrix. I had to do 3 operations, 2 multiplications and an addition to get this first value. 3 operations to get this value. It'll be the same here. That's 12 operations to get one product. Okay? Well, what about a 5 by 5 times a 5 by 5? How many operations would that be? Okay, interesting question. 225. It takes 225 very simple arithmetic operations, but 225 of them to accurately take the product of 2 5 by 5 matrices. Now do you see the problem? It's 225 operations, and what happens if you get 224 of them correct, but one of them wrong? Then the whole goddamn thing turns out wrong, right? Even worse, mistakes that we make in this, because again, this is just one product, tend to propagate. What that means is that when you make a mistake, it tends to turn into 4 mistakes, which turn into 20 mistakes, and eventually you get to something that's not even recognizable anymore. Okay? So we simultaneously need to develop a way to do this relatively quickly and also very accurately. Okay? This just takes practice. You need to practice these things. Okay? There's no other way around it. Now, fortunately, they're nice, simple, basic operations. You're going to get good at it eventually, all right? But I'm warning you now to put some actual practice into that, okay? Let's go ahead and finish off this product, all right? And I'm not going to write down the dot products here. We're going to do them. Verbally. So I'd like the 2-1 entry, row 2, column 1. So I will take row 2 and dot product by column 1. So row 2, column 1, -1 times 1 is -1. 1 times -5 is -5. -1 plus -5 gives me -6. Okay? 2-2 entry. That's row 2, column 2, right? So row 2, column 2. -1 times 2 is -2. 1 times -2 is -2. Add those, you get -4. And there's my product, right? So this is how we multiply matrices. Okay? But let's talk about what just happened here. Okay? I took every row in my first matrix and multiplied it times every column in my second matrix, and those dot products had to line up, right? For example, I can't take the dot product of, let's say, 1, 2, 3, dot 2, 5. I can't do it because they're not the same length, right? Dot product doesn't work. That means for this multiplication to work, I have to have the same number of entries in every row in my first matrix that I do in every column in my second matrix. Well, what does that mean? It means I might have some issues with this operation being defined. So let's say that A is an M by N matrix. Okay? And I'd like to multiply it times matrix B. Okay? So this is M rows and N columns. Now note that N is the number of elements in every row, right? If you have 4 columns, then there are 4 entries in every row. Okay? So this is the number I want to focus on, the N. Okay? There are N entries in every column, and for every one of those, I need to have at least one entry in every column for B, so that number of rows. In order for this product to make sense, B has to have n rows. For a product, these are called, okay, these are called the inner dimensions. And if they're not the same, then this product can't even be done. I'll show you an example in a second, right? Well, what about the number of columns for B? Well, that actually doesn't matter. I mean, anything you want, right? Okay. But I can tell you then the size of the product. Okay? If you multiply an m by n matrix times an n by p matrix, then the result is going to be m by p. Where did I get those values? Well, those are the outer dimensions. Okay? All right, so these are the outer dimensions. Okay? Okay, fine. All right, so we just need to track whether or not we can do some of these products, right? So for example, let's say I take this matrix here. This is 1, 1, 2, 3, 4, -1. Can I multiply these two matrices together? Well, no, and that seems weird, doesn't it? I mean, they're the same size. Shouldn't I be able to multiply them together? Well, no. Unfortunately, this one is 3 by 2, and this one is also 3 by 2. The inner dimensions don't match. I mean, look at trying to take a dot product between this row and this column. How do you take a dot product between 1, 1 and 0, 1, -1? Doesn't work. Okay, we don't have enough entries, right? So this doesn't work. Okay, fine. But this one would. Okay. Let's say I want to take a product of, how about this one? So let's say 0, 1, -1, 1, 1, 1. That's just the transpose of the previous matrix. Okay. So these are two different sizes. It's kind of weird, but this one's 2 by 3. I can actually do this product. I can multiply these two matrices together. Okay. This is a 3 by 2. That's a 2 by 3. These inner dimensions match, right? So I know I can do this multiplication. How big will the result be? I don't actually want to do, well, we can do it. We'll go ahead and do the product. If I'm looking at the dimensions here, remember these outer dimensions, these give me the size of my product, so it should be 3 by 3. Okay, well, let's do that real quick. 1, 1 entry, row 1, column 1. 1 times 0 is 0, 1 times 1 is 1, add them, you get 1. 1, 2, row 1, column 2, 1 times 1 plus 1 times 1, that gives me 2. Row 1, column 3 for the 1, 3 entry. 1 times -1, 1 times 1, add those, you get 0. 2, 1 entry. 2 times 0, 3 times 1 gives me 3. 2, 2. 2 times 1, 3 times 1, add them, you get 5. 2, 3 entry. 2 times -1, 3 times 1 gives me 1. 3, 1 entry. Row 3, column 1. 4 times 0, -1 times 1, that's -1. Okay? 3, 2. Row 3, column 2, 4 times 1, -1 times 1, that's 3. Last one, 3, 3 entry, 4 times -1, -1 times 1, that's -5. So there's my product. Now notice this is even a different size than my previous ones. Now this is a problem. Okay, so I mentioned a property before. Okay. Let me reiterate it. There's a property called closure. Okay, closure is a mathematical property that basically says the thing that comes out of an operation looks basically like the things that we put into it, right? This is not closed, okay? The product is not the same thing as what I stuck into it. It's not closed, right? Why is closure important? Well, we like closure because closure allows me to repeat an operation, okay? Let me give you a quick example, okay? As an example, there are two different multiplications for vectors, right? There's the dot product, u dot v, and the cross product, u cross v. The first one is not closed, okay? U dot v gives me some scalar k, it's a number, right? The second one is closed. The cross product of two vectors is in fact another vector. Now why would I want closure? Because this doesn't make sense. U dot v dot w. I don't know what the hell that means, right? Because once I take a dot product of the first two vectors to give me a scalar, I don't know what the hell the dot product of a scalar and a vector is, right? This is not actually defined. I can't repeat this operation, okay, because it's not closed. On the other hand, repeating cross products is fine, right? Yeah? I can do u cross v cross r cross s cross t. I can cross 15 vectors in a row and it's fine because every time I do that, I get another vector out and so I can cross product that with the next vector. Okay? So this is a bit of a problem, especially if we want to use these things for anything sort of approaching algebra. Okay? I got to be very, very careful that I actually have defined operations. Now you'll notice, and I left my very first example here on the board, and this is not always the case. It's not always unclosed. This is a 2 by 2. This is a 2 by 2. And the result is a 2 by 2. In general, matrix multiplication is not closed. But if you multiply two square matrices, then you get a square matrix of the same size. So multiplication of square matrices is closed. Okay, so that's very, very important. Okay, all right. So we have multiplication. We have our properties here. I want to talk about a couple other properties and then an identity for matrix multiplication. So I talked about for addition and subtraction and scalar multiplication that all the normal properties you can think of hold. They're associative. They're commutative. There's a distributive property, things like that. For matrix multiplication, we lose some of those. Okay. Let's talk about which ones we get to keep. We get to keep associativity, right? So if the following is defined, so assuming A times B times C, assuming that's actually defined as a matrix D, remember there might be some issues with closure, but we'll pretend they're not. Okay, it is associative, right? So this is fine. This is perfectly okay, right? So if you have three matrices multiplied together, it doesn't matter which two you pair together first. That's okay. What it is not, however, it is not commutative. A times B does not equal B times A. This is a problem, okay? So in general, they are not commutative. This is a big problem, okay? It's a big problem. I got to keep that in mind. Why? Well, now all of a sudden there's a difference between left multiplication and right multiplication, right? Now when I want to multiply by a matrix A, I need to decide whether I want to multiply it on the left or multiply it on the right. As an example, let's say we're in the middle of some sort of algebraic expression. So I've got something like matrix B times variable vector X is equal to C. And let's say I would like to multiply both sides by A. Well, what I can't do is this. That's not okay, right? I mean, sure, I can multiply by A, but I can't left multiply on one side and right multiply on the other. That's not okay. So now I've got to be very careful with my algebra. Okay? If I want to multiply both sides by A, it's got to be something like A times bx, so that's A on the left, and then A times C, also A on the left. All right? So be very, very, very careful. Okay? Again, not commutative. The direction of our multiplication matters now. Okay. So, we lose one more property. We have a very nice property called the zero product property. Okay. This states that if A and B are real numbers, we're going to focus on real numbers here. It actually applies a little bit broader than this, but let's focus on real numbers. If A and B are real numbers, then A times B equals 0 implies that A or B is 0. Okay? So if I have a product of two things and they're 0, at least one of them has to be 0. Again, this is true for real numbers. It's true a little bit broader than that, of course, but that's what we're going to sort of focus on here. This no longer holds for matrices. Okay? Suppose I have matrix A times matrix B, and this gives me the 0 matrix. Right? Remember, it won't give me the number 0, it'll give me a matrix full of zeros. But let's say I have A times B, and it gives me a 0 matrix. I have no idea whether or not either one of these two matrices, A or B, is 0. They could both be non-zero matrices, and the product could still be 0. That's unfortunate, but, well, we'll work around that, right? And in point of fact, there's a whole field of mathematics based on how to solve for things like this. Okay, so we know what we lost here. Everything else holds. You can still distribute, right? Distribution still holds. So if for some reason you have A times B plus C, that's fine. It's A times B plus A times C, but remember, it's left distribution, so the A ends up on the left. Okay? All those things are fine. Okay? What about my identity? Sure. Okay. So what about A times some mystery matrix? What mystery matrix will give me A? Okay. Well, the mystery matrix in question, we're going to call I. Okay. We're going to call this I sub n. Now, why n? Well, I need to know the size of A in order to tell you what the identity is. So let's say A is m by n. Remember, n is the number of columns. If I multiply it times this matrix I sub n, I'm going to get A. So what is I sub n? I sub n, it's defined this way. This is called the Kronecker delta. Ugh, I hate that terminology. Okay? But this is defined as delta I sub j is equal to 1 when I is equal to j and 0 otherwise. This is a very convoluted way of explaining what the hell this thing looks like. Let me show you an example. I3 is a 3 by 3 matrix that has 1s on the diagonal and 0s everywhere else. I2 is a 2 by 2 matrix that has 1s along the diagonal and 0s everywhere else. What do you think I4 looks like? Good job. It's a 4 by 4 matrix with 1s on the diagonal and 0s everywhere. This is what the multiplication identity looks like, right? If you take any matrix that you can multiply by this matrix I3, and you do, then there will be no change, right? Again, in the actual algebra, when we write I, we typically won't write I2, I3. We'll typically write I, and when I write I mean whichever one is the relevant size, right? Like if I need I4, that's what I means at that point in time, right? Okay. We got to be a little bit careful when we come down to addition then to make sure that things are well defined. But when I stick in an identity, I mean whichever one is relevant for this multiplication. So this is not terrible, right? These are my identities for all the different forms. Okay. And remember, that's determined by whatever size you need to make the multiplication work. Okay. Let me give you the index definitions for these things because you might need them for proofs, okay? Later on when we do some proofs in the semester. They're fine, predominantly. The multiplication one's not great, but they're fine. So let's talk about addition. Okay, so if I have, I'm going to put some matrices up here. So let's say A is the collection A sub ij, and B, collection B sub ij. Okay, and again, here we go. So for addition, it's pretty easy. A plus B. This is just A sub ij plus B sub ij. Again, we're just writing them in component form. Scalar multiplication. We've got some scalar R times A. This is just R times A sub ij. Again, multiply it times every component individually. And you have matrix subtraction. You can piece together a definition from these two, fine. Or we can just write it like this. A minus B, A sub ij minus B sub ij. Okay. Again, just subtracting the corresponding components. These are fine. All right, this is perfectly reasonable, and honestly, you probably could have puzzled that out on your own. Let's talk about actually multiplying. Now remember, for multiplying, I'll have to define my matrices a little differently because again, the matrices don't have to be the same size. Okay, I just need their inner dimensions to be the same. So let's say A is M by N, and we'll call this A sub ij, and B. Hold on, I don't know what they use as their other end. I want to use the exact same definition they use in your book, down to the letter, because this one's not pleasant. They use N by P. Okay, so B is N by P. Okay, again that's B sub ij, just indices. Okay, then if A times B equals C, then C sub ij, so this is the ij entry for the product, okay? This is the sum. What's the dummy index they use? Is it K? It is K, okay? The sum from K equals 1 to n of a sub I k times b sub k j, and this is ranging over all values of I and j. We'll just put for every I and j. Okay. I ranges from 1 to m, and j ranges from 1 to p. I really should, you know what, I should clarify that. Because the j is coming from the b columns and I, so let's say 1 less than or equal to I less than or equal to m, and j ranges from 1 to p. Okay. So this is just the definition for this. It's not pleasant. I don't expect you just to memorize it and regurgitate it, but it is entirely possible you might need it for a proof at some point. Okay? So again, when you need it, you have it. Okay? All right. Let me talk about one more thing, and that'll be the end of what we have today. As normal, there will be homework assignments for this, some ways for you to practice some of these operations. Please make sure that you actually put some dedication into practicing these, mostly because, again, this is arithmetic and it gets taken for granted. And when it gets taken for granted, then we eventually find out that we're not exceptionally good at it, right? Okay. We had an operation before called transpose. That's from the previous lecture. Okay. And I'd like to talk about how transpose interacts with some of the things that we've done so far. So let's say you have A transpose and you take another transpose. Remember that transpose swaps the rows and the columns. And so A transpose, so if I swap the rows and columns and then I swap them again, well, it makes sense that should just be A again, right? It should invert itself, right? Okay. How about with addition? Let's say I have A plus B, and I want to transpose that. That's fine. This is just A transpose plus B transpose. Seems good, right? How about multiplication? So I've got A times B transpose. So I can't do this. This is not okay. This doesn't work. Why? Why doesn't this work? So this doesn't work. Well, the problem is A has to be m by n, and B has to be n by p, right? Inner dimensions have to match, but the outer dimensions don't. If I transpose them, if I do A transpose, that would be A, it'd be n by m, again, swapping the columns and rows. And B would be P by n. I don't know that m and P are the same. So this doesn't work, right? Yeah. So it turns out for multiplication, you've got to make a little adjustment, right? So A times B transpose is B transpose A transpose. The order of the multiplication changes. And this is actually fine. All right, guys. Again, today was just a bunch of properties, definitions for arithmetic. Please make sure you practice these, actually put some effort into it so that later on in the semester when you need to actually utilize these properties, they'll be somewhat second nature to you. Okay? All right, see you next time.